Hello everyone, welcome to the stream. Today we're going to be looking at an algorithm called the Dijkstras Algorithm, and we're going to be implementing this in C++. So let's say that you were playing Plague.Inc., that great game. It's super not relevant right now, but let's say you wanted to transmit your disease from China to America. I don't know, I can't say that. That's too topical right now. I can't say that. Maybe China to Connecticut. No, it's even worse. Sorry, my mistake. But let's say you were playing Plague.Inc., or you were making an AI to play Plague.Inc. for you. That might be what's happening now, but you never know. So let's say you did want to find the shortest path from China to America. What you would find is that you can do it with your analytic methods, but to program a computer to do it, it becomes a bit more difficult. So that's where Dijkstra comes in. This dude he practically is computer science. Like, where's Dijkstra? This man, Edgar. Where's his a list of the shit he did? He did so much. Here we go. Is this it? No. He did a lot, though. So, Dijkstra's algorithm is essentially based on graph theory. And this is essentially a graph of nodes, where each A, B, C through F, G, I can't spell, are individual nodes. And these numbers here represent the weights between two nodes. So, essentially the distance. It could be kilometers. It could be imperial distance units, but regardless, he came up with a way to find the shortest distance between two nodes, or from a starting node to any other node. So if we have a graph like this and our starting node is A and we want to get to E, well, the shortest path, we could look at this. So we have 3 and 7. Well, first we want to find how many different possible ways there are to get there, and there are many. So there's A to C to E. 3 plus 7 is 10. So I'll just say equals 10. Or let me just write that. So 10. We have A to B to E, which is 8. And we also have A to B to G to E, which is 7. And the A to B to G to E happens to be the shortest distance from A to E. And you might be wondering, well, you go across more nodes, but the thing is, there are different weights. This has a 7 here. This is a 7, while this is only a 1 and a 1 here. So it does get annoying, but through this algorithm, it should make a lot of sense. So let me just erase this stuff right here. And once we actually do all this stuff out, what we should get is something called the shortest paths tree, where if we want to get from a starting node, which will be A, so start, and our end goal is any other node, we just have to follow this shortest paths tree to get to that node. So let me zoom out a little bit. So in this algorithm, we'll be using this table here, and let's say we wanted to get from A to E, A to E. So what you would do is we'll go along that path. So A, B, G, E. This is what our end goal should look like. So so with this table here, we'll essentially be mimicking this in our code, where we will use parallel arrays. It's not the most efficient, but it is good for learning purposes. So we have a node array, and then we have a weights array. So the weight array represents the shortest distance to this node along this shortest paths tree from the previous node. So we're essentially going to go ahead and backtrack. So we start at E. It has a weight of 1, and the previous node is G, according to the shortest paths tree. G from B to G is also 1, so we go to G, put a 1 for the weight, and the previous node is B. And then from A to B, it's going to be a 5, and the previous node is going to be A, and from A to A is 0, and the previous node is also going to be A. So what we'll get is something that looks like, let me just fill out this table. This is what our final table should look like. So then D is 2, E, and F is 1 from E. So if we wanted to get to any node, we would essentially just backtrack along this table like I just did with E. So if we wanted to get to F, what you would do is you would go to F, and you wanted to calculate the distance, you would take this weight and then go to the previous node, which is E. E has a weight of 1, so 1 plus 1 is 2. Then go to G, which is 1, so 1 plus 1 plus 1 is 3. Then go to B, which is 5, so 8. 3 plus 5 is 8. Then you go to A, which has a weight of 0, so the total distance from A to F is 8 along the shortest path tree. So we'll be mimicking this in our code, but let me first show you guys how we're essentially going to do this in the code. So we'll have a fourth array for our visited nodes. So this will just keep track of all the nodes that we have visited, so we know that they're at the shortest distance possible. We'll have a queue, which will represent the nodes that we haven't completely checked yet. So yeah, so let me just go through this program right now with a pen and paper, or a pressure pen and a drawing tablet in my case, and hopefully it'll make more sense. So in the queue, we start with these starting nodes. So A: 0. So we take the weight of A and from the starting node and put it in here. So A0. And then in every iteration of Dijkstra's algorithm, we're going to go into the queue. We're going to get the node with the minimum weight, with the smallest weight, and then we will delete it from the queue and put it onto the visited area. So this is what it's going to look like. So we'll start with A. So right now it's the smallest one because it's the only one there. So A0, smallest. So you cross that out. You bring the 0 up to we start out with a 0 and A in the weight. So you bring that up to the weight into the table, A0, and then you put A in visited, like that. And then you go to the map of nodes and you find the neighbors of A. So right now, B is a neighbor and C is a neighbor of A. There are no other neighbors. So what you're going to do is you're going to bring all of its neighbors down. So, I put B: C. So it's B: 5 because that's the weight, and C: 3 right now. And there will be special conditions on what to do with each neighbor, but right now this was the first node that we did, so those conditions won't be present. So we essentially do the same thing again. We find the smallest distance, so it's 3 in this case. So we cross out 3. We put C in visited. We add that weight to the node, or to the table. So C, 3, and then the previous node will be A. And we put all of C's neighbors. So C has D and E as neighbors. So we bring down the B with it, and then we put a D, and we have to calculate the total distance from the start to D. So it's 3 to C and then 7. So D 10, like that. And then C's other neighbor is E, which is 7. So 3 plus 7 is also 10. So E: 10. And then in the next iteration, we're going to do B this time. So cross out B, bring B up to the table. So it has a weight of 5 and previous node is A. And this time we're going to do something a little different. So B has 3 neighbors: C, E, and G. C is already in the visited array, so we're going to ignore it completely. E is in the queue. So what we're going to do is we're going to calculate the distance that it takes to get from A to E along the path A, B, E, and then we're going to see if that new path is shorter. And if it is, we're going to accept it and we're going to put it in the queue, and otherwise, if it's longer, we'll reject it. So let's check this out. So from A to B to E, we calculate the distance as 5 plus 3, so 8. E, so let's actually just bring everything down. So we have D10 will be brought down, E10 will also be brought down. And now we're going to calculate the new distance from A to E. So 5 plus 3 is 8. So we're going to accept this new path. So what you do is you cross out the 10 and you make it 8 right there. So now that we know this is the shortest path possible. And then the last neighbor is G, and it's not in the queue, nor is it in visited, so you just add it to the queue. So G is 5 plus 1, 6, like so. We look at the smallest one, which is G. So we take G, take the weight from B, so it's 1, and the previous node is B, like that. Cross it off the list, add G to visited, and then we go and add all of G's neighbors. Well, G only has E as a neighbor, so we once again have to calculate the new path from A, B, G, from G to E, or along the path from A to G to E, and then we'll see if that's shorter than the 8 over here. So let's see. We have, so we're going to essentially backtrack through the table. So we start at 1, so we have 1 as the weight, and we go to B, which is 5. So wait, no, that's wrong. We're calculating the path from E. Okay, so we essentially backtrack from E to A through the path E, G, B, A. So we start at E, and then we have a 1 weight to G, which will be the previous node. And then G is in the table, so we essentially can calculate the distance from there using this table. So a 1 plus a 1 in G, and then we go to B plus a 5. So 1 plus 1 plus 5 is 7. That's smaller than an 8. So we're going to bring down the D, bring down the E, 8 right now, cross the 8 out and make it a 7 because we found a shorter path. And then that's G's only neighbor. So we go into the next iteration. And this time E7 is the shortest one. So we cross that out, put E on the visited node. I never put B on there, I'm sorry. So before G and E, you want to put a B because we already added that. So we're going to put E on the visited array. You're going to put, and now we're going to add the data for E to the table. So the node E is 1 away from G. So we have a 1 and a G there because that's the shortest distance that we found. And then the D, and we need to add all of E's neighbors. So let's see. E has a neighbor of F and D. So F will, well, let's bring down the D first. And then we have F, which is just a 1 plus E. So 1 plus 1 plus 1 plus 5 is 8. So F colon 8. Like that. And then D will just be the distance from A to E. So 7 plus 2, which is the weight of E to D. And because it's already in the queue, we're going to accept this new path since it's shorter. So D9, just like that. And then the last one, or the last two, cross out F. F has no neighbors. F has a weight of 1 from E, like that. Put F in the visited queue, and then we're left with a D9. And 9 will be the last one. It has a weight of 2, and the previous node is E, and then we're left with none. So we essentially repeat this iteration until the queue is empty. So this is Dijkstra's algorithm, and now you can see how we can backtrack from this into this. So if we wanted to find G, we're essentially just going to go to G, put a 1 there, and we go to B. So put a 1 from G to B. You essentially just connect the node and its previous node with its weight. So we can draw this out. So let's start with G. So G is up here, and it has a connection to B, which is its previous node of 1. F has a connection to E, so we'll just do E first. So E has a connection of 1 to G. F has a connection of 1 to E. Oh, I can't draw. We also then have D, which has a connection of 2 to E. C, now B has a connection of 5 to A. and C has a connection of 3 to A. So this is our shortest paths tree right here. And if we wanted to, like I said in the beginning, if we wanted to go from A to another node, we would essentially just follow the shortest paths tree. And the principle of the shortest paths tree is that there's only one path pointing to it. There can't be multiple paths pointing to it, but there can be multiple paths coming out of it. So with A, you have 2 paths coming out of it. With E, you have 2 paths coming out of it. But you cannot have 2 paths going into an array, or into a node. All right, now let's dive into some of the code. All right. Okay. I am just looking through some of the stuff here because he did do a lot. Like, all right, let's just get into the code on it. All right, let me put my tablet away at this point. I'm gonna flip the music on. Let's do some volume beta. How about that? Because we did this album in the last stream where I spent 3 hours studying for my midterm. That was so fun. All right, let's start at concrete halls. All right, that's way too loud. Hold on, let me. Can you guys? I hope you guys can hear this. It is on, but this is very low. There you go. All right, go into Visual Studio, and let's get this started. Okay. So first thing we're going to do in any C++ program is create our hello world statement. So I'm just going to do include iostream int main std hello, and I'll do Dijkstra this time. So let's go ahead and run it. We don't need any libraries for this. It's just going to be pure math. All right, press that to close. All right, so first thing I'm going to do is we're going to include a couple of libraries. So after iostream, do include limits.h, or let's see. Yes, limits.h, because we'll need a maximum. We'll need to access the maximum value of an integer. Just turn this down a bit so I don't mute myself out. Next include we'll need is vector. So include. Why is this there? Include. You guys can't see that because this thing was in the way. Include vector like that, and then we'll include that. So in vector, we'll need that for the queue because we'll just be adding stuff. We can't have an array for that because we'll need a dynamic size for it. And then with math, we'll need access to the pair class. Okay. So I'm going to write a couple of. I'm going to write a single utility method at first, and then we'll go right into it. So we're going to create a template method, type name T, so because I want to find, I'm going to go into, this method is going to be called contains, and we're going to test to see if a vector has a certain element. So vector of T, like that, and it's going to return a boolean. So it's going to return a standard find. The first iteration, so v.begin. The last one will be v.end, so we want to go across the whole vector. And then the value we want to find is x, and we just want to make sure it does not equal v.end, like so. So yeah, that's your simple contains method. Next, we're going to want to define a name. So for the queue, we're going to be using a vector, and it will be a vector of pairs, because if you remember, we'll need 2 values in each thing, but a map will not be. I don't think a map would be too. I think a vector would just be easier in this case. So a vector of pairs, pair of an int for the index of the node, and double. Just like that. And because we don't want to type this out, we're going to create a typedef. This essentially allows us to call this by something else, and I'm going to say min pq. So now what we can do is do min pq, or why did I say min pq? Q, and so now we can say q, like that. So this is the same as putting this whole thing right here, but because we did a typedef, we don't have to call it by this entire thing every time. All right, all right, so now we want to construct our map. So the first thing we're going to have is a array of characters, just because these are all single characters. And we have to define a size for this, so we're just going to have a global definition. So define, and it's going to be v for the number of vertices or nodes, and it's going to be 7, not y, 7. So we're going to have a char nodes of size v, and it's going to take, and it's just going to be A, B, C, D, E, F, and G. Like so. And next we're going to create our graph. So it's going to be a 2D array as a 2D array for doubles. So it'll be double graph v is equal to. So essentially what this is going to be is it's going to have the node on the left, on the rows, and the distance to other nodes in the columns. So let me show you an example. So let me start with A. So if is there a way to, or I can't really, here, let me just put this, or let me put Chrome off to the side for now. Okay. Alright, let me just, there. Alright, so in the first row we'll do A. So A has 2 neighbors, B and C. So the distance from A to A is 0, or we don't really consider that in here because it's not a possible route as of now. So distance from A to A is 0. Distance from A to B is 5. The weight of the distance from A to C is 3. And then A has no other neighbors, so we're just going to put zeros for the rest of them. Like that. So essentially what this is going to look like is, so it's going to be A, comma B, comma C, comma D, G. Like that. So that's going to be the distance of the neighbors, but you only account for the neighbors, not the total distance. So for B, it'll be 0, 0, 2, 0, 3, 0, 1. I don't know why it's not allowing me to indent right now. For C, we're going to have just D and E as 7. So 0, 0, 0, 7, 7, 0, 0. I know this is pretty inefficient. But for learning purposes, this is the best that we can do right now. Alright, for D, we have just 2 to A and that's it. Or 2 to A and 6 to F. Like that. For E, we have 1 to F and 2 to D and that's it. 0, 0, 0, 2, 0, 1, 0. now we're going to create two methods that allow us to print these arrays. So right here. So void print array, and this time this one will take the 2D array, so double graph, just like that, and it'll just essentially iterate through the rows. So in bars, 0, bars is going to be plus, and for C, equals 0, C is less than V, C++. Got him. That's a funny joke right there. And then we just want to print out the character. So graph at RC with a comma after it, and that's it. But no new line after that. But after the row, we want to print out a new line. All right. And then next we want to do the same method, but for a 2D a double pointer graph, because in methods we can't really return a 2D array. We have to return a pointer, a double pointer. So it'll be void print array, and it's going to be double star star graph. But it's going to be the same exact thing, so we can just copy and paste. It's weird, but in C++ you can't do that. Okay. So now that we have those utility methods out of the way, let's go ahead and actually get into the method. So okay, so in the main method, I just want to go ahead and print out the array. So print array graph at first, and then I want to just print out two lines like that. And then we're going to have a method. I'll create the template up here. So it'll be double star star Dijkstra. And it'll take in, what is it going to take in? It's going to take in an array of, no, it doesn't take the nodes. It doesn't care about the nodes. It takes in the graph, so a double. Yeah, for some reason you can do a 2D array in the parameters, but not as a return. And then int source. This will be just the source node. So for our cases, it will just be 0. So yeah, all right. So then in our main method, we're going to want to say double shortest paths tree, because that's what we're getting from this method. So Dijkstra. This array out shortest path tree, so make sure it did it already, and then just return 0. And then we'll just add a toto to test. Okay, so now let's actually write the Dijkstra method. Alright, let me just, oh, my dog's barking. I bet the mailman's here. So just let me go get my... Hold dog up. He's sitting on my lap right now. Barking too much, you boy. Okay, so in Dijkstra, we're going to create those parallel arrays. So we're going to have one for weight, so double weight at V is just going to be, we're going to initialize everything to 0. And then int, or no, actually we want to initialize these as int max. And then int previous node, this will be another array. and we'll just set those all to 0 for now. Like that, and then we want to say the distance from the source to the source is 0. So weight at source, so the source element in the weight, right? You can jump off me. So that distance is equal to 0. And then the previous node, source, is equal to 0. Or not 0, is equal to source. Because we're essentially just mapping the source node to the source node by itself, just like that. Okay, and then we want to have our visited log. So visited log, and that'll just be a vector with integers. This will be visited for now. And then this is going to be our queue right here. So because we have that typedef up there, we can do queue, like that. And like I said before, our queue is going to start out with just a pair of, just with the source node and 0. So queue.push back, we're going to be adding an element to the array, and it'll be a pair. This is why we need the mapping to pair of int and double. That, and we'll pass in the source, the index of the source node, and 0 because its weight is 0. Okay, so next we're gonna go ahead and iterate to find shortest path. Alright, so like I said before, the condition will be while queue.size is not equal to 0, and it will not start out as 0 because we pushed back. We added the source element, so the size will be 1 right now. Alright, so we want to get the smallest value. So I'm actually just going to template a couple of methods up top, and then I'll write them out later, but I just want to have them up here for now. Okay, so we'll need int find min on pq, and it'll take in on q, and it'll take in a q. We want to have int find on q. This will just be to find a certain element, so it'll take in a q and an element, and then we're going to want to calculate the distance. Double weight v int previous node v and int element, and then our final method, which we will use to test this, will be the same numbers or the same name. So calculate distance, but this time we'll just be passing in our shortest paths tree. And then int source and then int goal. Just like that. Okay, so I'm just going to write out the algorithm, and then we'll write out those methods, and then we should be done. Alright, let me go back here. Alright, so we want to get the smallest value. So int smallest is equal to find min on q, and we're going to pass in the q, just like that. So this will get us the smallest value based on weights, not the index, the weight. So the 0, the 3, the 5, the 6, the 7, 8, and then the 9. So this will return the index, the smallest value in Q. So we want to add to the visited list and erase from Q. So visited, push back, and then it's going to be smallest, and then it's going to be, this doesn't return the index of the smallest value, it returns the node index of the smallest value. So what this is going to look like, and then we want to erase dot erase, and then we want to find the so the way we erase it is we have to use an iterator again, so we'll go from the beginning. So I keep typing min pq because that's what I had in my test, but q is more. Oh, why are you whining? Stop whining. Do you want to get off me? Would you like to get off? So such a baby. Oh my god. You can get off this. Such a lazy boy. Okay. So we're gonna erase the nth index, so we're gonna go from the iterator at the beginning, and we're gonna add the index to it. So find on q, it'll be q, and then smallest. So this essentially finds that index. Oh my god, dog, please. 1 second, I'll be right back. Stop barking. There's nothing to bark at. Alright, boys, I'm back. Alright, where were we? We were at here. Alright, so this find on q method. This find on q method will return the index of the element. So the element is the index of the node, and it returns the index of that node on the queue. So we just want to erase that from there. And then we want to iterate over neighbors. So iterate over neighbors. So we're essentially the way we do this is we're gonna go through the graph. So we want to do for int I is equal to 0, I is less than v, I plus plus. Get first is so if the graph in the row of the current in the node that we're analyzing, so in the smallest element, and at I is equal to 0, this means that the neighbor doesn't exist. Did I misspell neighbor? Wait a minute, how do you spell neighbor? That might be the British spelling. I don't think. Oh, I'm wrong. Neighbor. That's British. God damn it. Alright, so neighbor doesn't that's how it is. So we're just going to continue. Likewise, if it's already visited, so if contains, we're going to use that method that we wrote. So if contains int visited, so we specify the template parameter as int, and we want to do I there. So else if contains already visited, so we're going to go ahead and just continue like that. Can I type? I can't type. Okay. Now, next thing we want to check is else if location, or not. God damn it. It's going to be find on queue. So if the location on the queue of the element of I is not equal to -1, we're going to know that it's in the queue. So this works because, remember, we're iterating through the graph. So let's say that we were looking at A. So we go to this row, start at 0. It doesn't have a neighbor of A. It has a neighbor of B. B is not in there, so we'll just add it to the queue. But let's say it was in the queue. So if we're looking at this row, for example, if this was in the queue, then we want to find that distance. So we're on I is in here, I is equal to 0, like that. So we're going to want to see if that's a bad example because A is not in the queue. So let's say it's F. If F is in the queue, then it's going to look, then it'll find the index of this in the queue, of this weight here. Okay, so it's in queue, find new path. Okay, so we're going to want to say the current distance, because remember we want to compare to see if the new path is accepted or rejected. So double current distance is equal to calculate distance, and we're going to do wait. We're going to pass in the previous node, and then we're going to pass in I, like that. And then the new distance, so double new distance, is it going to equal calculate distance to the previous node, so wait previous node, and then to the smallest, which is this node's parent, or the connecting node, and then plus the weight from the smallest, from this principal node to the neighbor. So that's represented through the graph of smallest at I, like that. And then we want to say if new distance is less than current distance, except path. So we're essentially going to erase this from the queue. So yep. I actually need to create this as a variable. Alright, so we just go auto loc is equal to find on queue, and then I. So else if location is not equal to -1. So if we accept the path, we want to erase this from the queue. So queue.erase queue.begin plus location, because we're going to update the value, but we can't really access a value and update it in a vector because they're not pointers. If this was a pointer, then we would be able to, but because it's not a pointer, we're just going to, if we say .at location, we're going to get a copy of the variable back, so it won't give us the actual variable. So min pq, or q.erase, and then q.push back, and we're going to pass in a pair of int and double, and it'll be I and then a new distance. And then we want to update the same thing in the table. So wait at I is equal to graph smallest at I, that's this thing right here, that's the weight of that connection, and then previous node at I is equal to smallest, because we found a more efficient path. Alright, let me get a quick sip of water here. Alright. Alright. So that is if the thing is in the queue. Otherwise, we just want to add it to the queue. So if it's like if it's a new node that we haven't thought about yet, all we're going to do is do add to queue. So we need to set the values in the table. So wait at I is equal to graph smallest I, and then previous node at I is equal to smallest, and then q dot push back standard pair int double, and then I, and then we're going to pass and calculate the distance, because remember in the queue we want to take the whole distance, not just the weight of the link connecting this node to its previous node. So calculate distance, weight, previous node, I. Wait a minute. Oh, yeah, that does work because this isn't we're passing the previous node array. I misread my code there. Okay, so yeah, this essentially gives us outputs this table right here. When we're all done, when it's done with all the iterations, it will output this table over here. So after this, we want to go ahead and once the queue is empty, so this will run until the queue is empty. We want to generate our shortest path tree. So generate shortest path tree. Alright, so we're going to do because we can't return a 2D array, we have to return a double pointer, so shortest path tree is 0. So essentially what this is saying is we want to set it initially to 0, and then we want to set the first pointer to an array. So this is essentially set it to an array of pointers, which we will then set each of those pointers in the array into another array. So it's kind of weird, right? So for int r is equal to 0, we're going to go through each thing. So r is less than v, r plus plus. We're going to say shortest paths tree at r is equal to a new double, so a new array of doubles. And then for int c is equal to 0, c is less than v, c plus plus. And then we're just going to set each element equal to shortest paths tree at r, and c is equal to 0. And I can't just say set this equal to an array of 0 because it's initialized. It won't have the proper length. Yeah, because this will give us it's a null pointer. Because this technically is not. It's hard to explain what. We need to initialize each pointer as an array. Double. Okay. So next we want to go ahead and just input final values into the array. Alright, so the way we do this is we'll just go through each node. So int I is equal to 0, I is less than v, I plus plus. So we want to say shortest path tree at previous node, so in the row of the previous node, at I is equal to wait at I. Because, like in the initial array, this row represented node C, and this represents the distance from C to D. So we're only going to output the distances on the shortest paths tree into a new array that looks just like this. Alright, so this, why am I getting an error? Double. Oh. And then just add an add I there because it's a 2D array. And then when that's all said and done, we can just go ahead and return shortest paths tree. So you can also see in this loop here is that because we're only iterating through each node once, each node will only have one thing pointing to it. So yeah. Now we can go ahead and talk about the other methods that we have not written yet. So we have all of these, and I'm just going to go ahead and copy them all down. Like that. We'll start with find min on Q. Alright, so this is the way that you usually find a minimum value use in an array. you just go, you set the current minimum to the first value, so it's equal to q dot at 0, and because this is a vector of pairs, we can say dot first dot second, because that's the actual weight value. And then the index of that will just be dot at 0 dot first, because this is a pair, or the first part of the pair represents the index of the node. And we're essentially going to return the index at the end. So we want to iterate now through everything in the queue. So for int I is equal to 1, because we're starting, since we already covered the 0th element, we want to do the first element now. So I is equal to 1, and we want to set the size equal to q.size. I is less than size, and then I++. If we were to do I is less than q.size, that would call that method each iteration, so that would be a little inefficient for the code. So you just set the size in the initialization, and it makes it more efficient. All right, so we want to test to see if the weight is smaller than the current minimum. So if q.at i.second is less than min, then we have found new min. So we say min is equal to q.at i.second, and then we need to update the index. So idx is equal to q.at i.first, like that. And then we return the index of the node. All right, next is the method to find the index of an element on the queue. All right, so this will be for int I is equal to 0, size is equal to min pq, or q.size, I is less than size, I plus, just like that. And then we're essentially, this is just going to be a linear search, right? So because it's not sorted in any way. So if min q.at i.first is equal to the element, just return I. Otherwise, we just want to return -1 to see if it's not in the queue. Okay, now we're going to write the calculate distance method. So this is going to be a recursive method because, like I said, the way we did it up here is we essentially backtracked. So we started out at our goal and we backtracked to the source. Right? So because it's recursive, we have to have a condition that will end it. So if previous node at element is equal to the element, then we just return 0, because the distance from element to itself is 0. And otherwise, just return the weight at the element plus this method, calculate distance, with the weight, previous node, and then we pass in the previous node at the element. So we're going to essentially pass in the parent node from there. And then the final utility method will be calculating distance based on a graph, given a shortest paths tree. All right, so the way we're going to do this is it's going to be recursive again. So if source is equal to goal, return 0. I'm just going to write the same comment. Distance from source to goal to itself is 0. And next we want to find the row with the goal as a neighbor. So for int r is equal to 0, r is less than v. I gotta turn my vibrator off. Wait, no, don't take that the wrong way. I gotta turn my ringer off. It's I didn't get much sleep last night. I really didn't. Alright, so we're essentially going to iterate through each row and then see if shortest paths tree at r at goal does not equal 0. This means that the neighbor exists. Am I spelling right yet? Alright, and if it does exist, we're going to return the weight of this current branch. So paths tree at R at goal plus this method called again, so calculate distance. And we're going to pass in this shortest paths tree, and then source, and then R. R will be the row that contains it as a neighbor, so it'll be the parent node, or the node that got us to this. So yeah, that is all the utility methods, if I'm correct. And the one thing I do want to do before is I do want to create a callback or a type name for this standard pair, just because. So I'll say typedef, and I'll do, what should we call it? Q element. I'll just say Q element. Just because Q, these last 4 letters are silent. And we can also put this in a namespace. So namespace Dijkstra, just because so we can so we can distinguish these from standard namespace. So Dijkstra. And then we also I can just put this method in the namespace as well, just because. And then so it'll just be Dijkstra like that. And then when we call it, we just want to do and then we're going to find all the pairs that we used. So this will be Dijkstra Q element, and then the same thing here. So Dijkstra Q element, and then we'll just want to do this Dijkstra right there, and then Dijkstra like that. Alright, nice. So this should work. I hope it does, because if it doesn't, I'm going to break my computer. Alright, good. Let's go ahead and test this. That looks right. That looks right. Let's compare it to our shortest paths tree. Alright, so starting in rows with A has neighbors with B and C, which we have here, and have the weights 5 and 3, which is good. B has a neighbor with G of length 1, which is right. C has no neighbors. D has no neighbors. E has a neighbor with F and D of weight 2 and F of weight 1, which is right. F has no neighbors, and then G has a neighbor with E of length 1. So we fucking did it. Let's go. That is quality code right there. So that is nice. So now let's go ahead and test the actual thing. So in main, let's go ahead and test this. So let's go ahead and say int start is equal to 0, int goal is equal to 3, and we're going to go ahead and print. So we'll do a new line, and we'll do nodes at start, 2 nodes at goal, and we're going to print out the calculate distance. So calculate distance, shortest paths tree, start goal, like that. Let's run this again, and so A to D is 9. Let's verify that real quick. So we start at A. So A, 5, 6, 7, 9. Perfect. All right. So everything works perfectly. So this is something that, like I said before, people use to find the shortest distance from China to the USA. This is used with TCP networking, where you want to find the shortest distance from one server to another server across broadband cables. It's used everywhere. Pathfinding algorithm, pathfinding AI, like video games. How does an enemy know to get to you? And the way we could also use this I'm currently doing my OpenGL tutorial. If we do end up creating like a pathfinding algorithm with AI, these nodes would have to adapt to know that there's objects in the way. So what you would represent as an object in the way would be a node you could not go from A to B if there was a node right there. So you would have to determine that as well, but the same principle applies. We could also, in another video I might want to do this, is create a more sophisticated representation of this graph right here. But I tried that and I wrote like 200, more than like 300 lines of code, and it didn't work. Oh, look at that, 200 on the dot. I was running the walls, but not AI walls, but I was running into difficulties, and so yeah, it wasn't really working all that well. But I don't know, I'll keep trying, but who knows. Alright, that is all I have for you guys today. I'll probably put out another stream later this week on the second OpenGL tutorial, sixth OpenGL tutorial, where we will start putting stuff on the screen. So yeah, I'm looking forward to that, and I will see you guys then. Bye.